Welcome to section 1.2, where we kind of discuss what makes science different from everyday life. What makes science special. And so when we talk about science, one of the key things about science is trying to be objective. What this means is you need to come up with some way of measuring and understanding the world that everybody else should be able to get the same answer, should be able to agree upon. And so when we talk about objectivity, we'll oftentimes talk about this idea of trying to make things quantifiable. And that just means come up with a number. So instead of just saying so-and-so is tall, we might say they are 6 feet 3 inches tall. Because that tall idea might vary. If you're 7 feet tall, I might see someone who's 6 foot and say they're short. But if I just give it a number, everybody should come up with that same number if they're trying to figure out something about that person. And so this isn't like, poetry or art where it's subjective, where you can say this is great, or you can say that this means something to you, but somebody else is just like, no, I don't like it. We're trying to come up with things where everybody says, yes, that appears to be red, or even more specifically, that appears to be this particular wavelength of light. That's the idea behind objective, so more universal. Then it's self-correcting and collaborative. What this means is there's a process called peer review. And this is where scientists, if they're doing actual science, they'll publish their work. They put it out there so other people can check them to make sure what they did was correct. And if it's not correct, they can then give their own experiences, they can then give their own data so that scientists can continue working on it until they come up with an agreed upon consistent answer or consistent data that we can all agree upon, that we can all evidence, remember this objective idea, so we can all say, yes, this is what we're all getting now, so we can understand the world better. Even if you're a well-intentioned person, sometimes you make mistakes. So this is why it's so important, and this is one of those critical things about science, is you have to put your stuff out there to let others check you. And others will try and falsify, prove you wrong, is kind of how this works. And if everybody else says, oh no, I can't, that's usually when we start to get some acceptance as scientists, where we say, all right, we tried to shoot it down, it's still held up, it looks like, at least for right now, this is good. And then questioning is tied to this idea of self-correction. You'll see these are kind of linked, because as a scientist, you're supposed to question everything. You're supposed to not just say, I'll believe that because someone told me. You're supposed to say, show me your data. Now I'm going to go in my lab, or have somebody else that I know go in their lab and check it. And so we're going to verify whether or not that's right. We're not just going to believe you. So a scientist that sees the news where every other day they're talking about some cure for something or some miracle weight loss, scientists will sit there, I sit there, going, that's probably BS. They're probably taking and exaggerating. They're probably, misinterpreting some of these things. You need to wait and see. We don't just see some study saying eggs are going to kill you and suddenly scientists stop eating eggs. What we're doing is saying, all right, let me see the study, how many people were involved, are there other studies that show this? Until there's a bunch of things that normally support something, scientists usually remain skeptical about stuff. And then lastly, with science, we're normally trying to understand or improve something. So there's something out there that either we have an issue with because we just can't figure it out, and so it kind of bugs us, or there's something out there that's a major problem. Like you could have people going blind because they're not getting enough vitamin A. And so you can have scientists then, in their mind, what our thought process is, how can we remedy this? How can we try and fix this? And so we start to come up with ideas of how that could work. We try to test them out. We try to, once again, get consensus amongst other scientists that this is working. And then we can apply those fixes to try to make people's lives better. Now, with pseudoscience, we bring this up because this is oftentimes masquerading as science. And so this can be a problem for scientists because you get people who get this science label applied to something that's just not scientific at all. And people use that if it doesn't work, for instance, like you take this pill that's supposed to make you lose weight and they say, oh, it scientifically shows, or, a study has proven this. And you think that science is telling you this will work. People are just using the guise of science. They're using some of the terms of science. And so that typically falls into what we'll call pseudoscience. These are not scientific at all, but they'll oftentimes pretend to be. And so some of the things that can indicate something pseudoscience is if there's evidence against it. There's lots of these weight loss things that just don't work. There's nothing to show that it works. You can go buy a magnetic bracelet that's supposed to improve your circulation, but nothing shows that works. There's data out there that basically says either that this is false, or in some case it could hurt you. It's doing the opposite effect of what you want. But this evidence against is normally just not presented, or they've come up with some way of misrepresenting things. And once again, there's usually that link to science, like, oh, you've got iron in your blood, so wear this magnetic bracelet and it'll pull the iron and somehow cause more circulation. When in reality, if you think that one through, it would just make all your blood pool around the bracelet. That doesn't seem like that would be beneficial. It just doesn't logically follow. So evidence against, one big strike. Not falsifiable. They come up with something that there's just no way to prove wrong. They're just saying there's this hidden energy that ultimately will slowly work to make things better. But even if you die, they might say, well, you would have died a month earlier. So there's no real way to prove this wrong. It's just there. So if you want to see if something's scientific, you should be able to ask, what would it take to disprove this? What would it take to make you say this is not true? And if there's no answer they can give, it's not scientific. I don't care whether it's gravity, evolution, there are things that we can find that scientists can tell you what those things are that would make us say, oops, all right, back to the drawing board. Looks like we screwed something up. So it has to be falsifiable. And then lots of things that are just vague, like the idea of energy. You know, energy has a specific scientific meaning, but a lot of people, if you're talking about some more like new age things, they use energy as this huge umbrella term for this weird, vague, esoteric idea of something out there that's just doing something. But that's the whole idea, is it's vague. So how can we test it? How can we know it? How can we understand anything about it? We can't, because you haven't even defined it enough so I know what I'd be testing. And so this idea of making things so vague that you really can't do anything with it is another method that you see in pseudoscience. And then lastly, misusing data. So this one's common when, I can tell you right now, in pseudoscience, people like to use quantum. They don't really know quantum mechanics, but they like this idea of quantum stuff. And so there's studies that show that weird things happen at the quantum level, but not at all like what they're saying. You know, the people in homeopathy, for instance, will say that quantum mechanics, this quantum theory, shows that, you know, molecules can affect other molecules, but there's not data to back that up relative to what they're saying. You know, they're misapplying stuff. So they like a term, they have this general idea that there's this weird thing going on. In the case of when you're talking about quantum mechanics, quantum theory, there are weird things going on at a small level, but then they try and take that weirdness and reshape it, reform it, and reapply it where it doesn't belong, because that way they feel like they can lend credence to it. And so you'll see a lot of times where people will just take data, actual scientific data, but they just will abuse it, they'll misuse it, they'll misrepresent it in order to try to make it link to theirs, to try to give their ideas legitimacy. And now I'm going to go just a tiny bit into 1.3 because this kind of bleeds into 1.2. And so we're just going to start, because in 1.3 we're going to discuss a lot about experiments, how we set them up, and the parts of them that there are. But to start out, I just want to do a brief intro into what you might have heard before as the scientific method, although right now I would normally call it the scientific methods because it's not absolute. Scientists don't have a checklist that they go through, but there are some general steps. You know, initially scientists have some question, it could be a problem, it could be something that they're just interested in, so it could be a curiosity. But I don't want you to think that it's something where it's always just this question that's given to you by a teacher or something. It's not. You might be curious and be like, oh, I wonder how this works. You know, for instance, you can have simple scientific ideas. My car won't work. So you obviously have a question, a problem, you have something you want. So then you might do research and try to figure out, well, can I come up with something that's already out there? Can I find the existing idea to solve this? And so you might come up with the fact that there could be lots of solutions, but you don't know which one applies to yours. So you've done your research, you've looked into it, and so now you're going to come up with, what am I going to do? And so for most people, this comes down to creating a hypothesis. Not always, but where you're going to make kind of a prediction and say, I think this is going to be, initially in this scenario, the battery. So I'm going to go and I'm going to replace the car battery, and then I'm going to experiment. After changing the battery, I'm going to try to turn the car on. And then ultimately, I'm going to get my data, which in this case will be the car turned on or it didn't, and I'm going to draw my conclusion. Was the battery at fault or was it not? So in this case, if the battery was at fault, I could then, for other people, let them know this so they could also repeat to see if their issue also happens to be the battery. Remember, you have to share. Part of this conclusion idea is that you'll publish. You know, you might be letting others know this is what it was. But you also might get something where you were wrong. It turns out it's not the battery. So then you just kind of go back if your conclusion didn't turn out perfectly. What you can do is go back on up to this hypothesis or research phase and say, all right, well, before it wasn't the battery, but maybe it just had a gas. So you might go up, get some gasoline, put the gasoline in, and run the whole experiment data conclusion again until eventually you get the right answer or just lose interest because you haven't found the right answer and it's been a while. But this is the general process that scientists are going to go through. There's something that they're at least curious about. They normally are going to try to figure out, well, does somebody already know the answer that I'm after? Does somebody already have the explanation that I'm after? And if the answer is no or not in all cases, that's normally when you start to say, well, maybe it works this way. Make a prediction usually, although sometimes you can just do an experiment to see what happens. Then you'll do an experiment, take your data, and use that to decide if you need to change things, or ultimately if you think that you found something cool, and then you'll publish to let other people verify you found something cool, or verify that your method that you tried originally is also false, because that's valuable. Knowing something is false works. I mean, it's useful to know that if your car breaks down, it's probably not, these 10 things that are causing it. That's useful things to know so that you can focus on what might be the problem. So that's kind of a brief intro into this idea of the scientific method, the idea of how scientists approach problems to try and solve them and get valid conclusions.